all times in a regulated way. The problem that we had before is nurses that work in the health department always have trouble monitoring each patient in the ward. They need to spend more time during working hours checking the drip to see whether it is finished or not. They also lack acknowledgement of the exact amount of the drip from time to time. So for this system, we have 4 objectives, which is to monitor the patient's platelet bag capacity remotely. Then second, to develop hardware for the project with reasonable price and function well. And third, to alert the patient's attendance when the platelet bag is almost empty. And lastly, to reduce an air embolism and infiltration on the drip.
In the flowchart, the Wi-Fi connection is required for the system to function. If the connection is connected, the display shows Wi-Fi was connected. Otherwise, it will show dot. After run the system by using BLINK apps, the nurse can switch on and off the program anytime. When the IV drip monitoring system is off, the buzzer and LEDs are switched off. In the BLINK and LCD, it will display switch is off, system is closed, and the system will begin again if the nurse switches on the program. What will happen is that the IV drip monitoring system will be on. The platelet will be sensed by the non-contact water sensor. The buzzer will be sound and the LED will light up if the sensor fails to detect a platelet. The nurse will receive the notification alert IV bag almost empty at the same time that the IV tubing will be clamped by the clamper. The system will start over when the nurse resets the program to change the new IV bag. It is because the buzzer and LED are always closed when the sensor detects a platelet blinks and the LED display will show operating platelet dripping and the clamper was unclamped. This program will be repeated until the sensor doesn't see the platelet, else the nurse will switch off the system.
The define directive is used to define a symbolic constant blink print which is set to serial, whereas include directive used to include the necessary libraries for the project. Next, the IoT platform that we use is BLINK. The BLINK template ID, template name, and authentication token are defined to configure the BLINK template. Finally, the characters or CHAR are declared to store the Wi-Fi network credential. The code shows that the number of interface pins of LCD at 13, 12, 14, 27, 26, and 25, while sensor connect to pin 4, LED pin to 5, and buzzer pin to 2. The variable sensor state is initial to 0. The next 3 lines create virtual pin of BLINK for an LED, a terminal, and an LCD display. Inside the connect Wi-Fi functions, Wi-Fi being SSID, pass is to initiate a connections to the Wi-Fi network. Next, a while functions will execute when Wi-Fi is not connected. It waits for 500 milliseconds and print a dot to the serial monitor. Indicates that it is still trying to connect. Once the connection is established, the functions print Wi-Fi connects to a serial monitor. Finally, the functions call terminal clear and LCD clear to clear the virtual terminal and LCD display in the BLINK app. The setup functions used to initialize the board before it starts running the main program loop. The connect Wi-Fi functions called connect the BLINK and ESP32 via Wi-Fi, as explained in previous. Next, serial being 115200 is called to initialize the serial communications at a bar rate of 115200 bits per second. Pin would initialize the sensor pin as an input, while LED and buzzer pin as output. Next, server attach 19 attach a server motor to pin 19 of the ESP32. The line of my LCD being 16 2 initialize the LCD display with 16 columns and 2 rows. Finally, my LCD clear is called to clear the LCD display.
Next, the code continues with what loop. Under this, the code will look and execute line by line. The blink.run function enables blink routine for keeping connection alive, sending data, and receiving data. Then, the if statement checks the state of switch, which initialized by pin number 1. This switch is turning off by the nurse using blink apps, and it comes to a temporary close of the system when the nurse acknowledges that IV bag is needed to be changed. The switch is turned on to continue the monitoring system. If the switch is low, the LCD will display message of switch is off, system is closed. After that, it turns off the LED and buzzer with digital write, while LED 1.off function is used to off the blink LED. The code will wait for 500 milliseconds with delay function. If the state of switch is high, then it will skip the if statement just now and straight away come to the else statement. The sensor FNC function is called and the monitoring system operates. Inside the sensor FNC function, sensor state is declared to read the state of sensor pin. After that, we use if-else statement to check for the sensor state. If the sensor state is low, which means it's not detecting any platelet, the system will alert the nurse and patient. Firstly, blink.log event function will run and a push notification will send through the blink apps to notify the nurse. Next, the LED and buzzer include the LED 1 and the blink will turn on. The LCD will display alert, IV bag almost empty. Lastly, the run servo function is called to run the servo motor and wait for 1 second. If the sensor state is high, which the platelet detected, then the system will back to normal monitoring state. It turns off the LED and buzzer, terminal and LCD will display operating, platelet dripping, and reset servo function is called. The run servo function is to clamp the IV tubing when the IV bag is almost empty to stop the dripping of platelet. Servo right move the servo motor to an angle of 5 degrees and wait for 50 milliseconds. The reset servo is to unclamp the clamper so that the IV drip can be continued. An angle of 20 degrees is moved by the servo motor to open slightly of the clamper and wait for 50 milliseconds. So, let's take a look on how the project works.
Finally, our automatic LT platelet drip monitoring and alert system has proven to be effective. We were able to accomplish every goal we set out to achieve. This makes things easier for the hospital nurses who have a lot of work to perform. Our device has a limitation where it can only monitor one IV bag at a time. We hope to upgrade this system so it can monitor more than one IV bag. For future modification, we need a stronger and more precise clamper to enhance the system. For instance, a positive clamper could be used since it can last longer. Second modification is that we can add one more sensor at different levels so the alert system can alert the nurse twice as the platelet is running low. When platelet reach level 2 after level 1, clamper will do its work to stop the dripping. This
This is Drip Assist Infusion Rate Monitor, which also operates as a device that we make, but it can only display the drip flow without controlling the dripping.